Our next speaker in this session is Brian Hensel. He works with Gannett Fleming, and he's going to talk about the Route 30 emergency landslide repair, the use of technology to expedite action. So Brian, please.
Can you see that? Can you see my screen? I don't know what I do.
Yep, we can see you. You're good.
Awesome. Look. Oh, no, I did. I'm sorry, hold on a second. Let me try to get to my notes here. Okay, so thanks for the introduction, Dan. I'm Brian Hensel. I work at Gannett Fleming, and I'm going to talk to you today a little bit about some of the technology that we use to expedite a emergency landslide remediation that took place in 2018, and for the Pennsylvania Department of Transportation, and one of our contractor partners was Golden Triangle Construction. And just for those of you that might not be familiar, this is in East Pittsburgh Borough, which is about 12 miles east of the city. The Route 30 is a major thoroughfare for commuters, maybe not so much now, but they have 30,000 cars a day travel to and from the city. So I'll give you a little bit of brief background about the project. Gannett Fleming has an open-end geotechnical contract on-call services for the Pennsylvania Department of Transportation. They had been investigating a suggested subsidence condition out on Route 30. We were asked to come out and help them, assist them with what was going on out there. So we spent a couple days, and within 2 days we identified that a retaining wall and the slope was displacing and was not a subsidence event. We had some lateral displacement and both the slope and a mid-slope retaining wall. So we immediately evacuated all the residents below in the local community, and then within hours of the evacuation, a catastrophic landslide occurred. Now, we won't go into the specifics of the landslide here. I'm going to concentrate on the technology used to accelerate our design and remediation. And like I said, here's a view of the slide. 35,000 cubic yards of material cascaded down over the slope, 90 feet high, and directly impacted 2 apartment buildings and severely damaged 1 home. Overall, a total of 34 residents were affected and 10 were permanently displaced. So what do we do? Immediate actions. PennDOT has, again, an emergency contractor on call. They came to the site actually the night before it failed, and when we were attempting to unload the slide at the roadway, they began excavating material, but unfortunately the slide occurred too quickly, and so we went basically from an investigation to a remediation design. Immediately the contractor switched from excavating the road to excavating landslide material, carefully going through some of the residents' belongings, etc. We also had PennDOT's on-call emergency drilling contractor on site, and with the excavation contractor and the drilling contractor, they began to do core borings throughout the slide. And based upon some conversations with PennDOT, we had committed to put together the best set of plans that we could to remediate the slide, begin construction within 2 weeks. And there were other things going on like utility relocations, traffic detours, public relations, and of course the resident accommodations. Now, for some of the technology aids we used to help us accelerate the project, as with the majority of our emergency slide projects, we typically rely on readily available LiDAR mapping that is available online through POSDA. And I give you the link here for your reference later. These are great maps for studies, but they're not necessarily survey grade. They give you 1 foot contours of whatever the latest mapping is of the area. And this occurred in 2018, and you can see here the map was developed in 2006, so it's a little bit dated, but which may be a problem in rapidly developing areas, but they were adequate based upon our reconnaissance of the site. Nothing was really, landform hadn't changed. So basically, I called the office, they downloaded the LiDAR cut sections, and they were laying on my desk that night when I got to the office. So what did I do? I used the POSDA mapping. Here's the cross sections that we cut that day, and included information from the 2 partial borings that we were able to complete prior to the slide. And I put some interpretations on there based upon my reconnaissance over the 2 days on site, and came up with some general sketches of remedial options that we could pursue. So, and although technology may assist you with advancing designs more efficiently, just want to put it out as a reminder, the basis for a sound geotechnical design always begins with an understanding of the site history, including the underlying geology and the geologic hazards. Now, fortunately, several of these resources are now available online through PADCNR Geologic Survey and the new Allegheny County landslide portal. The links are right there at your fingertips. And you also want to look at any previous site development records or core borings that may be available from the owner or a local municipality. Okay, so what do we do? We actually used drone technology to collect current site mapping. Gannett Fleming owns a drone. We had it out there within a couple of days, and the UAV collects photogrammetric views of the site, and then from there we can develop very dense 3D point clouds suitable for creating a final design digital terrain model. The technology was very useful on this project given the unstable ground conditions and the steep terrain. Conventional survey would have taken weeks and would have put surveyors potentially in harm's way. One note of caution when using drone mapping, it must be tied to ground surface control points obtained by conventional survey in order to position the terrain model at the correct global locations. That way, mapping shared amongst survey teams can use the same controls, and we ran into problems here. That's kind of why I bring that up. I'll talk a little bit about that later. So here we are using this available technology. We now have mapping of the pre-slide conditions with the LiDAR surface and the post-slide conditions within 4 days of the failure using our drone mapping. And this was very helpful in developing the geometry of the slide, identifying the magnitude of both vertical and lateral displacements. Now, some of this technology that I'm presenting are now commonplace, and as Jim mentioned, 15, 20 years ago would not have been possible. Now, this stuff is widely used for social media, but we also found that these applications were instrumental in advancing our subsurface data collection and design. We had core boring logs photographed and emailed to the engineers in the office as the data was collected, and core samples were photographed and sent via text with discussions of material and termination guidance could be provided by the design engineer or modified in real time if we weren't hitting the material that we were anticipating. We could extend the boring. We didn't have time to go back, so these were very instrumental tools. The field survey of the boring locations was very important in real time because we had the excavators out there removing landslide material, and they were creating temporary benches for us to access with core boring equipment. And then as soon as the core boring was finished, we'd have the surveyor go over there and pick up the location and the elevation, so we could use that for developing our subsurface model. And then the excavators would come in right behind us and take out the temporary bench that we had that they had installed just for the core boring operation. So the use of all this technology, along with the nonstop around-the-clock efforts by the design team, PennDOT, and the emergency contractor, allowed Gannett Fleming to fully develop a geotechnical design of the slide within 5 days. And this is just a typical section with the geologic cross-section and the ground surface and some sketch of what we were thinking about as far as a repair. And this is just an overview of what we actually designed. We excavated most of the slide material, replaced with a durable rock buttress, and erected a 20-foot high, 400-foot long anchor soldier pallet wall socketed 20 to 25 feet into the basal sandstone, and installed 100 kip anchors, also bonded 15 feet into the sandstone. So the contract was awarded, and Golden Triangle came out, and they first thing they wanted is our electronic files. So they requested from Gannett Fleming, and they used our DTM to prepare an excavation benching model electronically, and the model was then uploaded onto a machine grading guidance system on all their excavators. So the models allow the equipment operators to determine in real time the excavation depths and positions, assisted by GPS locators mounted on the equipment. Just real quickly, you see us standing around there on the one excavation bench. We asked the foreman, okay, I have the drawing in my hand. Where are we? So he had the equipment operator come over, put the bucket down. He said, okay, what elevation you at? He could tell us right there on the spot whether we were at the design grade, above, below, etc. Now, once that was completed, the geotechnical staff also had to go out and field verify the plan limits and modify the actual limits of removal based upon our visual observation of any remaining colluvium or slide material. And this photo just basically shows that we had to cut an additional 5 feet out of the design bench to remove some colluvium that still remained within the center of the old valley. Now, some of the other technology that was used during construction was also drone related. They used it as a construction monitoring tool. So weekly identified technologies of Bridgeville provided UAV services. The drones were flown periodically to generate 3D maps weekly to track the progress and quantities for progress payments. And this is where I go back to all these technologies, or the survey instruments specifically, have to be tied to common reference points. They didn't tie to our reference benchmarks or the contractors, so their DTM model was slightly different than ours, so we couldn't track them exactly. But if they would have got on our monitoring points, there were some discrepancies, of minor discrepancies, but that's just kind of a lesson we learned along the way. Now I'm just going to quickly go through, here's some of the examples of how the 3D mapping was used. These are 3D image of the beginning of the excavation. Here is a completed slide removal construction bench excavation. These are just screen captures that I made from 3D models. That's why you see some of the, the trees or whatnot are cut out. These are actually 3D images. And this is a 3D image of the rock embankment placement and retaining wall construction. And finally, here's an image of the completed earthwork. Now they take these images, convert them into contour plots. The contour plots can then be compared through 3D computer models to evaluate change. This is a contour of the beginning again. Here is the completed bench excavation contours, and then finally contours of the completed earthwork. So they take this information and they can track volumes, areas, quantities, production rates, etc. And now they have example. This is example cross section of, this was the original ground. Here's the excavated grade, and this is the final grade with the retaining wall at the toe. So, and the comparisons also enable the contract to evaluate the amount of resources needed to compare to the completion deadlines. If they're behind schedule, they need to run more shifts, add equipment and manpower, etc. So they can evaluate that basically in real time. This is
Ryan, just a note, you're at 15 minutes, so if you...
Yes, sir, I got 2 slides to go.
Great, thanks.
This is just a picture of comparing the contours of the actual slide from Deanna Fleming's mapping versus the finished product contours that were made during construction. So just to show, it's a very useful tool. Just one specific example here I wanted to show you that you can use this tool basically to track specific areas. They had specified materials going in here is foreign borrow. So, and you can track this versus time. And this is actually the beginning of the project here. This is excavating in that area. And then this is actual placement of the foreign borrow material. So you can track how much and when the material was placed. So it's very adaptable and upon any user setup. I think that's all I have. Questions?
Thanks very much, Brian. Does anyone have a question? Please enter it in the chat. So, we ever going to get some sort of LiDAR thing for the stratigraphy? Something that we can just get that kind of detail across broad regions fast? The underground stuff?
I mean, typically the stratigraphy, the marker beds we use are, generally mapping the Pittsburgh coal contours or the Ames limestone, or the Upper Freeport. I think those are the major marker beds, and there are, geologic contour maps available from I think there's through the Geologic Survey.
Yeah, it's on PASTA. True.
Right. But as far as updating that, I don't know. I mean, those are based on, underground mining and all different sorts of records of outcrops. Don't know that we have anything more precise.
Here's a question. Were there indicators a week or a month before the landslide started or was coming?
Again, I was only on the site for 2 days, and what the original concept is that their material was, the roadway was being undermined for some reason, and we went and tried to videotape a lot of the storm sores. There was a storm sore crossing right where through the valley. So one of the thoughts was the storm sewer was separated and we were losing material into the sewer, which would run down in front of basically there is actually right here, there's a Turtle Creek runs under Electric Avenue there. So all the flow goes subsurface from up on 30. But quickly, it was, within 2 days, and I didn't have a picture of the retaining wall. We did find that, and there were some old houses buried up into the hillside from pre-30 construction that were abandoned during the original 30 construction. So some of the abandoned foundations were there, and actually, like by the second day, the slope was actually breaking off pieces of the old foundation, and the old pieces were rolling down behind the apartment building. That also gave us an indicator of this is lateral displacement, not necessarily vertical.
Okay, this is going to be the last question for Brian. Question is, were valley stress relief joints suspected as causal factors for this slide?
No. Based upon some visual observation and from the couple of borings that we did, we knew that the Morgantown sandstone outcrops on the hillside above, and that was indicative on some of the geologic map showed this area had rock falls, which we attributed that to the Morgantown. But once we had drilled down, we determined that the interface between the Morgantown, I think it's the Shenley red beds, are below it. We hit claystone right away. So any subsurface units weren't massive, so there wouldn't have been any valley stress relief joints through the Shenley.
All right. Thank you very much, Brian. This is a great presentation. I mean, it's such a big landslide, most people probably had to reroute at least once because of this thing. It's really cool to see what you guys did to fix it.